In this class we are going to discuss about full adder. In the previous class we discussed about half adder. So here we are going to discuss full adder. As we know that half adder is a single bit adder, so now this full adder is also a single bit adder. But why we are choosing this full adder means we are having some limitations for half adder. Those limitations are, for example, when you are adding 2 bits, in next step, for example, if you are having a carry along with the 2 bits, you are not going to add with half adder. That means, for example, if you are having bits like this is a 2 bit number 0 and 0, this is another 2 bit number 0 and 1, and this is another 2 bit number 0 and 1. So these three are the 2 bit numbers, for example. So B value is 0 1, C value is 0 1. So now to add these two numbers, that means B and C, you need 2 half adders, because to add these 2 bits you need one half adder, and to add these 2 bits you need another half adder. So now in this case, after adding 1 plus 1, you are getting 0 with carry 1. But for second half adder, when you are used to add this 0 plus 0 and this 1, when you are used to add 3 bits, it is not going to add 3 bits. In half adder, adding of carry is not possible. That is the limitation of half adder. To overcome that limitation, we are having full adder. Full adder is always similar to half adder. The only advantage, additive factor in full adder is it is having carry addition. That means whatever 2 inputs are there in half adder, those are increased to 3 bits. The third bit is a carry from previous bit or anything. So see here, you can see the block diagram. So in this block diagram, you can observe this full adder is having 2 single bit numbers and a carry. So for example, if you are having multi-bit numbers, then for each corresponding bit location you need to use different full adders. So here this is a full adder with 3 inputs, where 2 are general inputs and 1 is a carry, and having 2 outputs, sum and carry. So here also carry and here also carry, that is why I named like input carry and output carry, C in and C out. So this is the full adder. Full adder is a arithmetic logic circuit used to add 2 single bit numbers with a carry. Now when you had a full adder, you are going to remember a circuit with 1 XOR gate and 3 AND gates. So here how we will design that circuit, we will see. So in logic circuit designing steps, we know that to design any logic circuit, so first of all we need a problem definition. Here our problem definition is to design a full adder. Full adder means which contains 3 inputs and gives 2 outputs like sum and carry out. So here I am making my truth table to satisfy this condition. So here in truth table, totally we are having 3 inputs and 2 outputs. In this 3 input combination, we may have 8 combinations up to 0 to 7. That means here 0 0 0. So every time we need to choose 4 combinations, because whenever you take an input bits, so all the combination you must take. So here 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0 and 1 0 1, 1 1 0 and 1 1 1 are the all possible combinations for 3 input bits. So here we taken all possible combinations for this full adder. Now we will see how this is going to add. So here just we are adding these 3 bits. So I am doing this procedure. In this procedure I am doing like first I am adding A with B, after that the result is added with C. In any addition, that means when I am adding A and B or the result is with C, if you had any carry, just place 1 in carry out place, that is it. So now I am adding 0 plus 0 plus 0. 0 plus 0 means 0. We are adding that 0 to 0 means 0 only. You had any carry means no carry in any step. So now in the same way 0 plus 0, the sum is 0. The sum is added to next bit 1. 0 plus 1 means 1 only. In this step also, in any case you are not getting any carry. So here carry is 0 only. So here also carry is 0. We are not having any carry here. So now, so here 0 plus 1 you are having 1. 1 plus 0. So this is also 1. So 0 plus 1 you are having 1. That one is added with 0. So then you are having 1 here. So here also you are not hearing any carry. So put 0 in case of carry out. So here 0 plus 1 sum is 1. This sum is added with this one. Then you are getting 1 plus 1 is equal to, in arithmetic addition, 0 with carry 1. Sum goes to 0 and you are getting a carry. So in this case this is equivalent to 0 with carry 1. So now here 1 plus 0 is equivalent to 1. This one again added with 0 means 1 only. So in any addition steps, here we are doing two additions. First is A and B addition, after that result is added with C in. In any case if you got carry, then you need to put carry there. So here 1 plus 0, 1, 1 plus 0, 1. So here you are not hearing any carry means you need to put 0 here. So now in this case you are adding 1 plus 0, that is equivalent to 1. So 1 plus 1, 0 with carry 1. So now this case, last but one case, 1 plus 1, 0 with carry 1. In this case sum is 0, carry is 1. In first addition itself you had carry means you just put that carry here and whatever sum is there, so write at side. So for that sum the next bit is going to add. That means 0 plus 0 you are getting 0 only. So in last step you are getting 1 plus 1 means 0 with carry 1. We know that in arithmetic addition when you are adding 1 plus 1 you are getting sum 0 and carry 1. When you heard carry you need to put carry there. And now sum is 0 after adding 1 plus 1. For this sum you need to add the C in bit. So 0 plus 1 means you are getting sum also 1. So this is the full addition, full adder addition procedure functionality. For this functionality you need to design the logic circuit. First of all, to design any logic circuit you need logical expression or Boolean expression for that relation. Here to design any Boolean expression you are making use of K-map here. So now how many variable K-map we need to consider means, so I am going to consider 3 variable K-map, because here we are having 3 input variables, that is why I am going to use 3 variable K-map. So see here I am going to consider 3 variable K-map. So here this is a 3 variable K-map. When taking 3 variable K-map, you just make sure about number of cells. When you take in 3 variable K-map, you are getting 8 cells. So here I am taking A, B, C in like this, A, B, C in like this. When you are having only single variable, then you are placing 2 combinations of that single variable, and when B, C in is there, so these cell values, combination cell values are 0, 0, 0, 1, 1, 0 and 1, 1. So now I am going to place values in this K-map. So first of all I am deriving K-map for sum. This is the K-map for sum. So here where sum is equivalent to 1, there you need to place 1. So here sum is equivalent to 1. When A equal to 0, B, C equal to 0, 1. So A equal to 0, B, C equal to 0, 1 means here. So now second case this one. When A equal to 0, B, C equal to 1, 0. So A equal to 0, B, C equal to 1, 0 means here. So B, C place is 1, 0 and A equal to 0 means here. So now, so here also sum is equal to 1. So where means A is equal to 1, BC equal to 0, 0. So A equal to 1, BC equal to 0, 0 means this place where you are having common point or common cell, that you need to place 1. So BC equal to 0, 0 and A equal to 1 means here, and now finally here you are having 1 in your sum place. Now that means A equal to 1 and BC also 1. So that means all ones place. So A equal to 1, BC equal to 1, 1 means here. So now here you are having total diagonal is covered. This is one shortcut I already told you in last classes in solving some problems. So here if any diagonal is covered, so if total diagonal is covered, then definitely you can take the XR of gates. So XR of variables. So here total diagonal, whatever diagonal is possible, those diagonals are covered. So that's why this is equivalent to, so here A XR, B XR, C in. So we can say this is equivalent to A XR, B XR, C in. Now in the same way we can derive the expression for C out, that means carry out. So for this also, how we got this carry means because of input bits only. So by taking K map of this carry out, you need to consider the input bits only. So in taking K map, I am considering 3 variable K map because, so for this carry also we used same 3 bits, that is A, B and C in. So I taken K map, 3 variable K map with A and B, C in. Okay. Now see here, where carry is equal to 1, when you are deriving the expression for carry out, so you need to see where carry out is equal to 1, there you need to put ones. So here I am writing combinations 0, 0, 0, 1, 1, 0 and 1, 1. Here the combination is 0, 1. So now here 1 is there at A equal to 0 and BC equal to 1, 1. So A equal to 0, BC equal to 1, 1 means here you are having 1. And now here is you are having 1, that means A is equal to 1, BC equal to 0, 1. So A equal to 1 and BC equal to 0, 1 means, so here you are having another 1. And another one you are having A equal to 1, BC equal to 1, 0. That means here you are having another 1. So BC equal to 1, 0 and A is equal to 1 means, so here you are having. So A is equal to 1, BC equal to 1, 0 and final one you are having at all ones place, that means here. So now after placing all possible ones, you need to group that ones. So here is there any quarter is possible? No, there is no quarter possible here. So is there any double possible means? Yes, 3 doubles are possible like this with vertical grouping and 2 horizontal grouping. So I grouped these 2 ones and these 2 ones and these 2 ones. Now we have 3 prime implicants. By adding the 3 prime implicants, you are going to get your expression for carry out. Now I am writing the expression for this prime implicant, that is here top side it is covering only one box, you can take as it is, sidewise it is covering 2 cells, so there is no combination here, you can leave that and you can write only top wise. So top wise, that is equal to B, C in, plus I am writing for this I am writing, so here sidewise it is covering only single cell, you can take as it is, like if this is equivalent to 1 means, so this is equivalent to A, and top wise it is covering 2 boxes, in the 2 boxes the combination is 1 here, see here, this 1 will represents B. So now the value here is AB, sidewise it is equivalent to A and top wise common is B, A into B we will write. So finally this final prime implicant we are adding here, so that is, so this one means sidewise it is covering A only and top wise these 2 boxes, again one is common but here second one is common, that one represents C in. So now you are writing A Cin. So here the expression for carry out is BC plus AB plus AC. So now the expression for sum is equal to A XR B XR C. You can design by using this, you can design logic circuit like this. You are having input lines A, B and C in. These are the input lines A, B, C in. Now if you want any sum, you can take XR of A, B and C in. So that means A, B and C in, you can take XR, then you are getting your sum. If you want any carry, that means carry out, then you are getting, so from AB, BC, CA. So that means A into B, you need to take AND gate, and B into C, you need another AND gate, and C into A. So you need another AND gate. All these three AND gate outputs are added. You are going to get, you need to take OR gate here, and you are getting C out. So for this expression, I taken AND gates for AB, BC and CA. So like this, for addition of all three product of sum of products form, I am taking this OR gate and I am getting C out. Like this, we are going to design this full adder by using truth table and K-map. First we taken truth table for full adder. When you are hearing carry, you are placing carry at carry place, and after that you taken K-map for both sum and carry. After taking K-maps and getting expressions, you are going to design your circuit. So by this way we can design any circuit by using logic gates and designing steps.